In this lecture, we shall consider numerical illustrations based on tests for a univariate and two univariate normal population. So this lecture will be divided into two segments. First, we will consider a numerical example, a real-life example for a one-sample t-test, and then in the next segment, we will consider a real-life example for a two-sample t-test. So we will start with illustration of a one-sample t-test. Suppose we have collected a random sample of 31 energy bars from a number of different stores to represent the population of energy bars available to the general consumers. The label on the bars claim that each bar contains 20 grams of protein. So we will conduct a t-test to see whether this claim is justified or not. So this is the data we have on the grams of proteins in the energy bars. First, before going into the t-test, we have to check the data, whether we can perform the t-test on the basis of this data set. Here the data values are independent. The grams of protein in one energy bar do not depend on the other. An example of dependent values would be if you collected energy bars from a single production lot. But here we have collected the bars from different stores, as we have mentioned in the question. A sample from a single lot is representative of that lot, not the energy bars in general. So here we have independent observations. The data values are grams of protein and hence the measurements are continuous. We assume the energy bars are a simple random sample from the population of energy bars available to the greater consumer. That is a mix of lot of bars. We assume that the population from which we are collecting our sample is normally distributed, and for large samples we can check this assumption. There are different ways of checking these assumptions, say Kolmogorov-Smirnov test, or even the frequency chi-square test can also be applied to check this. So we decide that t-test is an appropriate method for this problem. So we have checked our data. Now let us in a nutshell talk about how to perform this t-test. For the t-test calculations, what we need the averages, the standard deviations, and the sample sizes. We round the statistics to 2 decimal places. That is for computational flexibility or computational simplicity. Whatever computation we do, we round them off to 2 decimal places. We start by finding the difference between the sample average and 20. Why 20? Because it is claimed that energy bars will contain 20 grams of protein as marked in their labels. So for example, 21.40 minus 20 is 1.40, that is one difference, and so on. Next, we calculate the standard error for the mean. The calculation is like this. It is S by root n. So S we can calculate, and root n is root over 31. So that will come out as 0.456. We have to now go for the test statistic. So we have collected all the pieces of the test statistic. So we calculate the test statistic as T, the difference of standard error, that is 3.07. So what we have calculated the means that you can do in a simple computer or even with a calculator. The means, the mean and the standard deviation we have calculated, and the sample size we know that is 31. So we have computed T. Now, after looking at the value of the test statistic, we have to make a decision what to do, whether we accept that the claim is justified or not. That is what we have to do. So the test statistic comes out to be 3.07, as we have already mentioned. We decide on the risk we are willing to take for declaring a difference when there is not a difference. That means declaring a difference means we are rejecting the null hypothesis. When there is not a difference means the null hypothesis is true. That means we have to settle down what will be our type 1 error. Suppose we want to take 5% risk. That means our level of significance or type 1 error will be 0.05. So in statistical speak, we set alpha, the level of significance, to be equal to 0.05. In practice, setting your risk level should be made before collecting the data. So that means when we decide to go for a test, we first decide on the risk level, that is the level of significance or the probability of type 1 error. And then we will start performing the test. That means we will collect data, do the necessary calculations, find the value of the test statistic, and so on. We find the value from the t-distribution based on our decision. For a t-test, we need the degrees of freedom to find these values, because if you can recall, a t-statistic comes with the degrees of freedom, which is the parameter of the t-statistic. The degrees of freedom are based on the sample size. Now, in our situation, the degrees of freedom will be n minus 1. N is the sample size, which is 31. So 31 minus 1, 30 is our degrees of freedom. The critical value of t with alpha equals to 0.05 and 30 degrees of freedom is plus minus 2.043. Plus minus 2.043. Why are we taking plus minus 2.043, not plus 2.043 or minus 2.043? Can you tell us, I am giving a hint, can you tell us the answer on the basis of the testing problem? This is because here we are conducting a two-sided test. That means whether the mean protein level is 20 or not. So that is why the critical value will be plus or minus 2.043. We can find these critical values in a t-table, or in most of the softwares these values are available. We now compare the value of our test statistic with this critical value. So if you recall, the value of our test statistic was 3.07, while the critical value is plus minus 2.043. Now you see, our test statistic value is positive, so we will compare with plus 2.043. So 3.07 is obviously greater than 2.043. So we reject the null hypothesis, and that means that the mean grams of protein is equal to 20. This claim is being rejected. We make a practical conclusion that the labels are incorrect, the labels where the protein level were written. And the population mean grams of protein is more than 20. Now we come to the statistical details of what we have done so far. Our null hypothesis is that the underlying population mean is equal to 20. So we write H naught mu equals to 20. The alternative in a two-sided test like this will have the alternative that the mean is not equal to 20. So we write the alternative hypothesis as HA mu not equal to 20. This is a two-sided test, as we mentioned earlier, and can be clearly seen. We are testing if the population mean is different from 20 grams in either direction, that is more than 20 grams or less than 20 grams. If we can reject the null hypothesis that the mean is equal to 20 grams, then we make a practical conclusion that the labels for the bars are incorrect. If we cannot reject the null hypothesis, then it will mean that the labels of the bars may be correct. We calculate the average for the sample and then calculate the difference of the sample mean from the population mean, that is x bar minus mu. And we calculate the standard error as S by square root of n. The test statistic formula we already know, that is square root of n into x bar minus mu naught, that is the specified value of mu, which is 20 in this situation, by S, the standard deviation of the sample observations. And we denote it by capital T say. We compare the test statistic to a t value of our choice of alpha and the degrees of freedom for our data, and using the energy bar data as an example, we set alpha equals to 0.05. The degrees of freedom are based on the sample size and calculated as n minus 1, which is 30. Normally, the statisticians write the t value with alpha 0.05 and 30 degrees of freedom as t 0.05, 30, the way it has been shown in the slide. The t value for a t-sided test with alpha 0.05 and 30 degrees of freedom, as we have already seen, it is plus minus 2.042. Two-sided test, so plus minus. Now, there may be two possible results from our comparison. the test statistic is less extreme than the critical t-values. Less extreme than the critical t-values will mean the test statistic is not less than minus 2.042 or not greater than plus 2.042. That means it may lie between minus 2.042 and plus 2.042. In this sense, the test statistic is not significant or it does not take an extreme value. You fail to reject the null hypothesis in this situation, that the mean is equal to the specified value. In our example, you would be unable to conclude that the level for the protein bars should be changed because you now accept the null hypothesis. That means you do not have the evidence that the mean protein level is either much more than 20 or much less than 20. So we cannot say that the labels are to be replaced. There is another situation. The test statistic is more extreme than the critical t-values. That means that either the test statistic is less than minus 2.042 or more than plus 2.042. In this situation, you reject the null hypothesis that the mean is equal to the specified value 20. And in our example, we conclude that either the labels should be updated or the production process should be improved to produce on average bars with 20 grams of protein. So that means in two ways we can look at it. We can, if the production process is given, that means we do not have option to change the production process, then the labels are to be updated if we reject the null hypothesis. On the other hand, if we intend to produce bars, protein bars of average 20 grams of protein, then our test says that the null hypothesis is rejected. That means the production process is to be altered. That means some modification is needed for the production process so that the bars are of average protein level 20 grams. So you can see that this is a very interesting application of one sample t-test, and here we are actually dealing with a real life problem. So many such real life problems can be solved by testing of hypothesis. Now we will go to the next segment of our study, that is the illustration of two sample t-test. Let us take with a real life example. One way to measure a person's fitness is to measure their body fat percentage. Average body fat percentage vary by age. By according to some guidelines, the normal range for men, it will be 15 to 20%, and for females, it will be 20 to 25%. It is by some guideline, by some health guideline. Our sample data is from a group of men and women who did workouts at a gym 3 times a week for a year. Then the trainer measured the body fat for men as well as for females separately. So here we have two populations, mind you. So this is the data. We have men and we have females, and body fat percentages are given. Now, if you can recall two sample t-tests properly, is it necessary that the number of observations in the two samples will be same? If you look at the slide, here the number of observations are different. There are more observations for men than females or women. So is it necessary that for a two sample t-test, the sample sizes should have the equal number of observations? Yes, here we have two different sample sizes, and a t-test does not require that the sample sizes are to be equal. So let us examine our data first. We can clearly see some overlap in the body fat measurements for the men and women in our sample, but there are some differences as well. Just by looking at the data, it is very difficult to draw any solid conclusion about whether the underlying populations of men and women at the gym have the same level of body fat. So that is why we have to go for statistical tests. They provide a common, statistically valid way to make decisions so that everyone makes the same decision on the same set of data values. That means the procedure has to be objective in nature. Not that by looking at the data, I will conclude something and you will conclude in a different manner. But both of us, if we go for statistical tests, then we will arrive at the same conclusion. So that is why we follow an objective method. The data values are independent. The body fat of any person does not depend on the body fat of any other person. We assume that the people measured represent a simple random sample from the population of members of the gym. Random sample is a necessary, so we will assume that the data obtained is from a random sample observations. We assume that the data are normally distributed, which is another essential assumption, and we can also check this assumption. The data values are body fat measurements, so the measurements are continuous. So it is also satisfying the requirement. We assume that the variances for male and female are equal, that is, we assume that the homoscedasticity assumption is satisfied. The next question is, how will we perform this test? From the table, you can see that we have calculated the averages and the standard deviations of male and female separately, and the sample sizes are 10 and 13 respectively for women and men. Without doing any testing, we can see that the averages for men and women in our samples are not same. But how different they are? Are they so much different that we can say that the populations are also different in terms of their means? Or they're not so different? That we have to decide by the t-test that we will be performing. Are the averages close enough for us to conclude that the mean body fat is same for the larger population of men and women at the gym? Or the averages are too different for us to make this conclusion? That we have to decide on by performing the test. Let's go into the computations. The calculations begin with finding the difference between the two averages. We have already seen the two averages. Their difference comes out to be 7.34. This difference in our sample estimates the difference between the population means of the two groups. The actual difference in the means is estimated by this value 7.34. Next, we calculate the pooled standard deviation. But before calculating the pooled standard deviation, we will calculate the pooled variance, which is S square. We already know the formula. It is N1 minus 1 into S1 square plus N2 minus 1 into S2 square. The whole thing divided by N1 plus N2 minus 2. And for our data, it is coming out as 38.88. You can also check these calculations yourselves because the data is with you. So you can verify whether the calculations are correct or not. And it is always good to do the calculations yourselves. And that is why I omitted the calculation steps. Next, we take the square root of this pooled variance to get the pooled standard deviation, and that comes out as 6.24. We now have all the pieces for our test statistic. The test statistic requires the sample means, the sample variances, the pooled variance and the pooled standard deviation, and then the sample sizes. So we have all these informations. So we calculate the test statistic, and the value of the test statistic comes out to be 2.80. We have to check whether this value 2.80 is a significant value for rejecting the null hypothesis or not. Let us see. So we have to take the decision. We decide on the risk we are willing to test for declaring a significant difference, whether the difference between the sample means is significant or not. For the body fat data, we decide that we are willing to take a 5% risk of saying that the unknown population mean for men and women are not equal when they really are. So this risk is again the risk of type 1 error. In statistics speak, the significance level denoted by alpha is set to 0.05. And I will again stress upon the fact that it is a good practice to make this decision regarding the risk before collecting the data. We then calculate the test statistic, and we have already seen its value is 2.80. Now we find the theoretical value from the t-distribution based on our null hypothesis, which states that the means for men and women are equal. You can find the tables in most statistics books. There is also a book of table which is Biometrica table, and these theoretical t-values are obtained in any statistical software. To find this value, we need the significance level alpha, and what else do we need to find this tabulated value? Apart from the level of significance alpha, for finding the tabulated value or the theoretical value, we also need the degrees of freedom. So what is the degrees of freedom in this situation? It is n1 plus n2 minus 2. So that is 10 plus 13 minus 2, which comes out as 21. We compare the value of our test statistic, which is 2.80, to the t-value. The t-value is 2.08. Since 2.80 is greater than 2.08, we reject the null hypothesis that the mean body fat for men and women are equal and conclude that we have evidence that body fat in the population is different between men and women because our t-value is more than the critical value. We now go to the statistical details of this test. A null hypothesis is that the underlying population means are same. So we write the null hypothesis as H naught mu1 equals to mu2, where mu1 is the body fat average for men and mu2 is that for females. The alternative hypothesis is that the means are not equal. So we write it as H1 mu1 not equal to mu2. We calculate the average for each group and then calculate the difference between the two averages. We calculate the pooled standard deviation, and that will require the standard deviation or the variance of each group, and this pooled standard deviation is calculated by the formula which is shown on your screen. Now the question is, what if your sample size for the two groups are same? There is no problem with it. Actually speaking, the computational labor will be reduced if the two sample sizes are same. That is, n1 is equal to n2, and if suppose we say n1 is equal to n2 is equal to some n, then what will be the pooled mean? It will be nothing but the average of the variances of the two groups. The pooled variance will be nothing but the average of the two variances. You see, n1 minus 1 into s1 square plus n2 minus 1 into s2 square by n1 plus n2 minus 2. This was our formula. Now replace n1 by n, replace n2 by n. So in the numerator you'll have n minus 1 into s1 square plus n minus 1 into s2 square. And in the denominator we'll have 2n minus 2. So it will be the simple average of the two variances. So even if the sample sizes are equal, actually we should be delighted of the fact that our computational labor will be reduced. So in this case, the test statistic is, as we know, x1 bar minus x2 bar in the numerator, and in the denominator is the pooled standard deviation into square root of 1 by n1 plus 1 by n2. We then compare the test statistic 2 of t-value with our chosen alpha value and the degree of freedom for the data. Using the body fat data as our example, we set alpha equals to 0.05. The degrees of freedom on the basis of the sample sizes is 21. The formula shows that the sample size for the first group as n1 and the second group as n2. The statisticians write t-value with alpha equals to 0.05 and 21 degrees of freedom as t 0.05, 21. This is the standard notation. We can find from the table that the t-value with alpha equals to 0.05 and 21 degrees of freedom is 0.080. Now, there are two possibilities from this comparison. The first possibility is this: the test statistic is lower than the t-value. Then we fail to reject the null hypothesis of equal means. You conclude that the data support the assumption that the men and women have the same body average fat, same body fat on an average. What is the next possibility? The test statistic is higher than the t-value, what we had in our example. We then reject the hypothesis of equal means, and we do not conclude that the men and women have the same average body fat. So there are two types of conclusions may be done depending on the value of the test statistic and its comparison with the tabulated t-value. So what we learned in this section is that how one sample t-test and two sample t-test can be used in real life situations. We have taken two real life situations in our course of study today in this lecture, but there are several other fields of study which can be incorporated here. T-test may be applied to a wide range of data, not only this type of data for body fat or protein level, that is the health statistics, we can apply this data in social sciences, in biological sciences, even in biotechnological fields, and also in commerce and accountancy. So whenever we study these testing problems, we have to think of possible applications. On the other hand, when we have some applications in our hand, we have to think which test procedure will be applicable to solve this problem. Thank you.